Okay, good morning, everyone. Let's dive back in. You're working on the 10th and final assignment if you are an undergrad, and in assignment 10, you're going to be implementing a series of search processes. The first one is so simple, it's not arguably an evolutionary algorithm. Second and third one are. So by the end of A10, you should have the final wrapper around your onion, which has many layers in it. You have an evolutionary algorithm that's evolving control policies for robots that are inside a physics engine. Next Tuesday, after you've done assignment 10, I'm going to dedicate a fair bit of time Tuesday morning to talking about the final project, what our expectations are for that, and how you're going to conduct that final project over the final month of the semester. Same thing goes for the grad students. You're finishing up the fifth and final differentiable assignment. We'll also talk about expectations for those taking the course for graduate credit as well. There's a question from an undergrad about whether you're doing the differential assignments. The undergrads are not doing the differentiable assignments. If you want to tackle them, they're all there on Reddit. You're welcome to give it a try. Okay, any questions about assignments, differentiable assignments? Okay, back to bipedal locomotion, lecture 12, which we're going to finish up today, and then we're going to move on to open challenges in the field of evolutionary robotics, and in some cases, open problems in robotics in general. We haven't been building robots for a very long time. There's a lot of open problems that nobody knows how to solve yet. Here's hoping they do, so we've got robots that shovel our snow for us and stack our dishes for us, and so on. In order to have safe, useful, and autonomous machines working alongside us here in the real world at scale, we're going to have to solve some of these open problems that we're going to talk about in lectures 13 through 19, respectively. Okay, so back to bipedal locomotion. I hope some of you practiced your silly walks since last lecture. We feel as if we are experts in this particular form of locomotion, but there's quite a bit of subtlety when it comes to legged locomotion. We saw last time two different robots that strike very different extremes in the four desiderata of locomotion. We saw the Asimo robot, which is pretty stable, but uses a huge amount of energy to get around. We saw the passive dynamic walker, which is extremely energetically efficient, but is very, very fragile. There is a very, very narrow range of environments in which the passive dynamic walker works. We saw the hybrid dynamic walker last time, in which once they achieved a passive dynamic walker, which was a pure mechanical mechanism, no motors, no sensors, no electronics, just a mechanical assemblage of parts. They could then add a little bit of electronics, a few motors, to get the hybrid dynamic walker. Slightly less energy efficient than the passive dynamic walker, but by building in some motors that apply a little bit of energy, they could greatly expand the range of environments in which this particular kind of machine can operate. We ended last time by starting to look at an evolutionary robotics approach to this problem. I introduced it last time, but just to remind you, we're going to see a two-stage evolutionary algorithm. In the first part, where they're evolving the robot, they're going to be evolving just the morphology of the robot, because there is no neural control of the robot. Once they manage to evolve passive dynamic walking in the simulated robot that you see here, they're going to then thread slowly, or more accurately, they're going to allow the evolutionary algorithm to start to thread some neural control into the robot. So part one, evolve the body of the robot. Phase one, evolve the body of the robot. Phase two, evolve body and brain to increase the range of environments in which this machine can operate. That's the idea. Okay, we ended last time by looking at what aspects of the body exactly is this evolutionary algorithm evolving. We saw last time that there are a total of 22 morphological parameters. These 12, which dictate the geometry, the height, the mass distribution of the robot. and then an additional 10 parameters that describe the 5 springs that exist in each leg. 5 springs in the right leg, 5 springs in the left leg. Every spring requires 2 parameters. Its stiffness. Is it a big piece of steel that's very hard to compress or expand? So does it have high stiffness? Does it have low stiffness? Is it a slinky? Does it take relatively little energy to expand and compress it? That's stiffness. Damping is if you have a spring and you let go, how long does it take till it comes back to its rest length? The length that it tends to hang out at when there are no forces acting on it. A spring that wobbles back and forth for a very long time until it comes to rest has low damping. A spring that very quickly comes to rest has very high damping. For any given spring, you can set different values of stiffness and damping and get different kinds of spring properties. Okay, so we've got 22 numbers that describe everything in one leg, on one side of the body. We only need 22 numbers because the biped, like us, is bilaterally symmetric. Whatever is being described for the right leg is exactly the same for the left leg. So they don't need 44 numbers, we just need 22. Okay. Okay, so we can imagine now we have our evolutionary algorithm. We have a population of random vectors. Each vector is of length 22, and any given vector describes a biped with a slightly different morphology. So far, so good? Okay. I mentioned in phase 1 that there's only a body and no brain. There's a tiny little bit of a brain in phase 1. The reason why goes as follows. When we put any one of these passive dynamic walkers at the top of the declined plane and rotate one of its legs outward as dictated by one of these 22 numbers, the investigators are going to allow the brain inside this robot to give the robot a little bit of a kick. It is actually, strictly speaking, a hybrid dynamic walker. There's going to be a little jolt coming from the motors in the very first time step of the simulation, and then the motors are going to go quiet for all the remaining time steps of the simulation. Okay, this is the brain of this robot that's going to be gradually turned on in phase 2. Let's have a look at how this works. Here's the sensor layer here, and for some reason they drew this from right to left. We've usually seen this going from sensors to motors from left to right. Doesn't matter. We've got all our sensors over here. We've got some hidden neurons in here, and we have our 5 motors in here. We've got 2 motors acting at the hip that rotate the leg forward and back and inward and outward, like your hip. We've got one muscle at the knee, one motor at the knee, and we've got 2 motor neurons at the ankle that rotate the ankle up and down and side to side. Okay. You'll notice there's a bunch of hidden neurons. You'll notice there's a bunch of recurrent connections. And there is an additional neuron here that we have not seen before. This is a central pattern generator. You have CPGs distributed throughout your spine as well. Forgive me, but when you cut off the head of a chicken and it continues to run around, the reason why is because chickens, like us, have central pattern generators in their spine, and central pattern generators, as the name implies, they generate an oscillatory pattern over and over again. And in the case of the headless chicken, that's enough to allow it to move. Eventually, it falls over. Whatever the rest of your spinal column and your brain is doing while you walk, it's basically just correcting drift. Your central pattern generator is the metronome that's setting the beat of your walking, and it's sending commands to your motors. You're never walking over a perfectly flat piece of ground, so you need to correct that metronome from time to time. That's what the rest of your nervous system is doing when it's controlling bipedal locomotion. Same thing here. We've got a CPG up here. You'll notice this central pattern generator is sending out its signal, which is 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on. That signal is being sent along these synapses to hidden neurons, and those values then flow to the motor neurons eventually. Okay, we've got a whole bunch of sensors over here. I want you to just scan from top to bottom and just pay attention to the rightmost letter. You'll notice there's a whole bunch of A's and F's. A we've seen before. These are angle sensors, otherwise known as proprioceptive sensors. These the angle sensor neurons are outputting the current angle of the joint. And F we have not seen before. These are force sensors. All the F's are sitting not at the joint. They're sitting not at the motor. Force sensors are sitting on the springs, and they're recording the amount of stretch or the amount of compression of the spring. If the spring is at its rest length, those sensors are reporting a value of 0. If that spring is being compressed inward below its resting length, those sensors are reporting a positive value. And if the spring is being pulled beyond its resting length, those force sensors are reporting a negative number. You have similar sensors distributed throughout your body. They're known as strain sensors. And when you're literally stretching or your muscles are compressed as you're standing on the ground, you feel it. And when you feel it, that's information that's being reported by strain sensors distributed throughout your body. Okay, you'll notice there's an assortment of other sensors. We've got some rotational sensors here. So we've got rotation X, rotation Y, rotation Z. These three sensors are reporting the amount of yaw, pitch, and roll. Pitch, yaw, and roll. The three ways in which, this case, it's the hip, is rotating. You also have sensors that report how your body is rotated relative to the ground or relative to the force of gravity. Where are those sensors in you? Your inner ear, your vestibular sensor tells you information about how you're oriented, or at least how your head is oriented relative to gravity. Okay. They also included some acceleration sensors. So your vestibular sensor, the vestibular sense in you gives you actually a mixture of information about your head's orientation relative to ground and how your head is accelerating relative to ground. Okay. Okay. Let's come back to the central pattern generator for a moment. I mentioned that in this robot, it's bilaterally symmetric. Every morphological feature of one leg is copied in the other leg. Same thing with the brain. This neural circuit that we just described, there is one neural circuit embedded in the right leg and an identical copy of this circuit embedded in the left leg. You'll notice there's 5 motor neurons. Remember that there are 5 motorized joints in one leg. So we've got a robot that's got 2 identical halves of a brain. Okay, the exception to that is the central pattern generator, and that's why they drew it up here. These dashed rectangles here are meant to represent these 2 identical neural circuits. And then there's one and only one central pattern generator, which, as I mentioned, is operating as a metronome. It sends out a value of 1, and then it goes quiet to a value of 0 for a while, outputs a 1, a 0, and so on. What it's actually doing is sending 1, 0, 0, 0, 0, 0 to the neural circuit in one leg and 0, 0, 0, 0, 1 to the other leg. It's a metronome, but it's sending a signal in antiphase to the 2 different neural circuits. 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. You can probably imagine why. They're trying to set, or they're going to evolve the synaptic weights coming out of this central pattern generator to set the pace at which it walks. So far, so good? Okay, a lot of detail about morphology and neural control in this experiment. Okay, what is the fitness function? This is the longest one I think we're going to see in this course. Fitness of the robot, and the robot is, we take it to the top of the declined plane, we set all the morphological parameters as dictated in the genome and possibly aspects of the neural controller, and then we turn on the simulation and we see how far, if at all, the robot moves down the declined plane. D is the distance it moves down the declined plane. Makes sense. Why is this fitness function not F equals D? Why is it F equals D times something else, times something else, times something else, times something else? Given everything I've told you so far, if you were to run this evolutionary experiment and just use the fitness function F equals D, what kind of behavior do you think you'd get? We're trying to maximize the distance the robot moves down the declined plane.
So trivially just fall and slide maybe a little bit.
If I put you at the top of a declined plane and I asked you to get to the bottom as quickly as possible, dive head first, although it doesn't have a head. Dive hip first down the declined plane, or fall over and slide down the declined plane. Doesn't even really qualify as a silly walk, but it's definitely not bipedal locomotion. I'm going to guess that that's what the experimenters did first, saw their robots were evolving to fly hip first down the declined plane, and they started to add, or strictly speaking, multiply D by penalty terms. So the way to read this equation at a high level is evolve robots to do what we want, D, but don't do it in this way, and 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 don't do it in this way. There are 5 kinds of silly walks that they're going to penalize the robot for. Let's start with 1 over 1 plus t. T here is not time, it's the amount of torque that's used. Remember that torque means rotational force. So when they start to turn on the brain of the robot, values arriving at the 5 motor neurons are interpreted as torque, the amount of rotational force to apply at the hip, the knee, the ankle, and so on. In our biped and in you, most of the time you're trying to minimize the amount of torque that your muscles are applying at your joints. Yeah? So this term is trying to penalize non-passive walking, active walking. Walk as passively as you can. Yeah? Okay. So you'll notice they all have the same form of 1 over 1 plus something. This is a common way of writing a penalty term. When you get to your final project and you start evolving your robot to kick a ball or climb stairs or climb a ladder, you're going to very quickly see that the evolutionary algorithm finds a lot of ways to get your robot to maximize the fitness function, but not in the way you wanted. You're also going to have to probably add in some penalty terms. So why 1 over 1 plus? It's the best way to think of the penalty is you define some quantity, which in this case is T, or torque. Torque is the amount of force. It's always positive. The more of that stuff, the worse the behavior is. So when you're trying to quantify the bad things that your robot is doing, come up with a variable that you can capture and measure in the physics engine. Make sure that that variable is always positive, and the more positive it is, the worse the robot is doing. If you can guarantee that it's positive, then you're not going to get any funny behavior on the denominator. 1 plus a positive value is always kind of well behaved. If t could be -1, then you're going to get into trouble. 1 plus -1 is 0. You got a 0 on the denominator. The evolutionary algorithm tends not to deal very well with fitness functions that have infinite values. Yeah. So in all these 5 variables down here, t, x, z, r, and y, the more of these things, the worse the robot is doing at what we actually want it to do, which is walk passively down the decline plane. Okay, so use as little t, use as little torque as possible. And as the robot is moving down the decline plane, minimize the amount of hip rotation about the x-axis. So in this physics engine, x points leftward out of the left part of the robot's hip. We want to minimize the amount of rotation about this axis. So we do not want a robot that walks in this way. We're back to the Ministry of Silly Walks. So try and not rotate backwards and forwards too much. Minimize z, which is rotation about the vertical axis. Do not walk down the decline plane like this. This is bipedal locomotion, but not the kind of bipedal locomotion that the investigators want. Minimize r, feet rotation about the z-axis. We don't want the feet twisting like this as the robot walks. And also, by the way, we don't want hip rotation about the y-axis as the robot walks down the decline plane. You'll notice, and I mentioned this at the beginning of the course, perverse instantiation is very common. It's ubiquitous in AI and robotics. It pops up all the time. And what roboticists and AI researchers are often doing is playing whack-a-mole. So they probably ran their evolutionary algorithm with f equals d and got a whole bunch of behaviors they didn't want. So they put in 1 over 1 plus t. They still got behavior they didn't like. They noticed that bad behavior, put in another term, ran their evolutionary algorithm again and again and again, and eventually with 6 multiplicative terms, they got rid of perverse instantiation, and surprise, surprise, they got nice passive dynamic walking down the decline plane. Okay, you will probably have to play whack-a-mole as well in your final project. Okay, so I mentioned that this evolutionary algorithm is going to play out in a bunch of stages. In stage 1, during the evolutionary process, they're going to evolve these 22 body or morphological parameters, and they're also going to evolve the synaptic weights that flow from the CPG, the central pattern generator, to the motors. So let's go back to the brain for a moment. They're going to evolve these synaptic weights that go from the CPG to the motor. These weights, and so on. They're going to let the CPG emit 1 pulse. They're going to allow the CPG to emit 1 pulse to 1 leg in the first time step of the simulation, and then turn off the CPG. So this robot is a little bit hybrid. There's a little bit of a pulse right at the beginning. Okay, so during evolution, evolve these 22 body parameters plus this subset of synaptic weights. And during the evaluation of each genome, these 22 numbers plus the synaptic weights, during each evaluation, during each simulation, put that particular robot at the top of the decline plane, allow 1 CPG pulse, turn off the network, and measure D, T, X, Z, R, and Y at the end of the simulation, assign fitness to that genome, go to the next one in the population, next. Delete the ones that get low F, make randomly modified copies of the genomes that get a higher value of F, and continue until you get passive dynamic walking down the decline plane. That's phase 1 of the experiment. Questions? So far, so good? Okay, I know these co-authors, and I always give them a hard time whenever I see them because they did not supply any movies of their robots in action, which is a shame. So we'll just have to take their word for it and move on to phase 2. So at the end of phase 1, they now have a population of genomes, each one of which, or most of which, when embodied as a robot, leads to passive dynamic walking down the decline plane. But that's it. That's the only thing that robot can do. If they take that same robot and they put it on simulated flat ground, The robot doesn't walk anymore. So they're going to continue the evolutionary process now, and they're going to allow evolution to reduce energy efficiency a little bit. They're going to allow the motors to do a little bit more work, but they're going to gradually expand the range of environments in which this robot can walk. Okay, so what's going on during evolution? They're going to continue to evolve these 22 body parameters, and they're going to continue to allow evolution to evolve the subset of weights that lie between the central pattern generator and the motor neurons, but they're going to alter the fitness function. They're going to multiply this whole thing by another penalty term, 1 over 1 plus v. So they're tasking the evolutionary algorithm with continuing to maintain walking, but make sure v is as low as possible. What is v? V is the difference between the passive velocity. So they're going to now evaluate, in the second phase, they're going to evaluate every genome twice. The first time, they're going to build the robot at the top of the decline plane, measure how it moves down the decline plane, all of these passive velocities, how does it move down the decline plane. Then they're going to lower the decline plane. They're going to make the decline shallower. They're going to put that same robot back at the top of this shallower decline plane, turn it on again, and maybe it's going to walk a little bit differently because from the robot's perspective, it's now in a slightly different environment, which is going to produce a different set of velocities, and they're going to take the difference between these. What's the intuition here? What are they trying to do? What's the intuition behind 1 over 1 plus v? At this stage, they have a passive dynamic walker. Now they're starting to evolve that walker on a shallower and shallower decline plane as the evolutionary process unfolds. What's the intuition here?
They want the robot moving at the same velocity, so they don't want it sprinting ahead, nor do they want it just standing still. But whatever it evolved passively, just kind of like lock that in and keep going.
Exactly. So whatever it was doing at the end of phase 1, as you say, lock it in. Try and hold on to that way of moving and change that way just a little bit so that you can continue to move in these different environments. This is another big challenge in AI and robotics. It's known as catastrophic forgetting. So if you task a machine or a robot with learning or evolving some ability, in our case here in phase 1, it was evolving passive dynamic walking. Usually this is how we do things. We evolve a machine or train a machine to do one thing and then say, oh, and can you also do this other thing? What often happens, regardless of the kind of robot or the kind of machine learning or AI model that's in play, it tends to forget the old task at the rate at which it's learning the new task. Very tricky, actually, to get a machine to learn something new and not forget what it already knows. So as you were mentioning here, the intuition for 1 over 1 plus v is to guard against catastrophic forgetting. Hold on to the ability to do passive dynamic walking down the decline plane, but add the ability to walk with a little bit more of a kick on the decline plane, on the shallower plane, decline plane. So what do I mean with a little bit more of a kick? They're going to make another change in phase 2, which is during each simulation. In phase 1, the CPG was allowed to send 1 pulse to the motors. In phase 2, the CPG is now going to start to operate as a metronome. It's going to start to emit a value of 1 every once in a while and send that value to the right leg, then the left leg, then the right leg, then the left leg. But what should be the frequency of the metronome? Should it be, or should it be hard to say? For all of you, you have a slightly different frequency at which you bipedally locomote. It's a function of your height, your weight, your general level of fitness, and so on. So who knows what the right amplitude or what the right frequency is for this metronome for these evolving robots. And by the way, remember we have a population of them, some of which are taller, shorter, have slightly different mass distributions. So the investigators came up with a neat idea, which is let the robot tell its CPG the frequency at which to beat. Here's how it works. Okay, so remember that the CPG sends out a pulse at T0, the first time step of the simulation. Remember at T0, the robot is at the top of a declined plane with one of its legs out forward, and suddenly the CPG turns on and the robot judders a little bit, which starts to send it down the declined plane. They measure, the code running the simulation measures the number of time steps that elapse until the heel hits the ground, and that number of time steps becomes the frequency of the CPG for that robot. So whenever that heel hits the ground, the CPG is going to fire for the second time, and that second emission of a pulse from the CPG goes to the back swing leg. Up it goes, and the third strike of the CPG is going to come however many time steps elapsed between T0 and the first heel strike. Make sense? So we now have a robot in which there's a little bit of a jolt arriving at the motors every K time steps as hopefully it walks down the declined plane. So now we've got a full hybrid dynamic walker on our hands in phase 2. So far, so good? Okay. I mentioned there's 2 phases. There's actually more phases. This is one of these papers that just kept going. They kept adding new twists to the evolutionary algorithm as they went. At the end of phase 2, they now have a robot that can either walk down a declined plane in passive mode, only one pulse from the CPG, and it gets to the bottom of the declined plane. Or they can put the robot on flat ground, and the CPG emits a pulse, and when the robot's heel strikes the ground on flat ground, second pulse, third pulse, and it can walk in a hybrid manner on flat ground. So now we have a robot that's still quite energy efficient because it's walking similarly to how it walks down the declined plane, but it's a little bit more robust. This machine can walk down declined planes or flat ground. Okay, all good, but what happens if it steps on a little pebble or a little bit of ice? There might be something unexpected in its environment. This robot is completely blind, deaf, and dumb. It does not have any sensor information coming in, so there's no way it can recover from any hiccups along the way. So they continued evolving these robots with this fitness function and those bodies and that neural control, but now they're going to gradually allow the robot to evolve a sense of itself. It's going to start to evolve the ability to modulate or alter how it walks in response to its sensor values. At the end of phase 2, the only values that are flowing through this neural network are those from the CPGs to the motors. All of these synapses in here, all the ones that flow from sensors to hidden neurons, the weights or the values of these synapses are 0. It's blind. It can't feel, it's numb. It can't feel anything. Okay. So in stage 3, they're going to, quote unquote, reconnect the sensors to the neural network with very small connection weights. So what does that mean? I just told you that all these values are 0. Remember that the genome is encoding 22 body parameters plus all of these weights. They now tack on a whole bunch of numbers to the end of each genome in the population, where those numbers represent the weights of these synapses. They're random numbers, but they're random numbers that are chosen very, very, very close to 0. Why? Why not just set all of these synaptic weights to random values and evolve the robot to walk based on values from its CPG and incoming sensory information? Some of you may not be ice skaters. Let's assume we teach you how to ice skate, but we teach you how to ice skate blindfolded. Not an easy thing to do, but you can learn to do it. Once you've learned to do it, then we take the blindfold off while you're on the ice. What happens? It's not a trick question.
I guess you're just better at ice skating and you can use your other senses too.
You're not. The opposite. You're suddenly on ice, but you've only ever experienced ice skating without visual input. The minute this comes off, suddenly now you're watching the world flow past you in a slightly different way that you've never seen before. And by the way, you're kind of new to ice skating. You have to learn ice skating all over again. Similarly, at the end of phase 1, we have a whole bunch of robots that have evolved the ability to walk, but they've sort of memorized how to walk. They know how their CPG pulses should flow to their motor neurons so that they don't fall over. And then suddenly we turn on all the sensors and all of these values start to flow into the hidden neurons and mix with the values coming in from the CPGs. The robot no longer is going to be able to walk. But we know that most of the evolved robots at the end of phase 2 can walk when all of these values are at 0. So let's start by moving them randomly away from 0 by a very small amount. You're out on the ice, you're still blindfolded. We replace your blindfold with another blindfold where you can see through the fabric a little bit. You can see flowing blobs of color go past you. We're trying not to surprise you. You're staying upright on the ice. We're going to gradually let you thread information back in, right? If you're learning ice skate because you want to play hockey, you got to be able to see the puck. But you learned ice skating with no senses, so we've got to let you be able to see and, by the way, keep skating so that you can use sensory information to do other stuff while on the ice. So far, so good? Bit of a tortured metaphor here, but hopefully you get the idea. Okay. All right, so we're in phase 3 here. We've now extended the genome to include all these sensor to hidden neuron synaptic weights. We're going to then continue in phase 3 doing what we've been doing in phase 1 and 2. We're going to continue to allow evolution to evolve the 22 body parameters. So maybe it's continuing to fine-tune the height of the robot, its mass distribution. Evolution is tinkering with all the synaptic weights now. And we're still using 1/1 plus v. During phase 3, we want to make sure that the robot doesn't learn sensor-based walking, but forget how to do hybrid walking without sensation and forget how to do passive walking without sensory feedback. So far, so good? Okay. In the simulation, same thing as before. A pulse from the CPG at the first time step, second pulse when the heel first strikes the ground. That sets the beat of the metronome, and off it goes. Okay. We don't have a video, but at least we have a figure here of how the most fit robot walks at the end of phase 3. Let's see how this works. We've got simulation time on the horizontal axis here. This is not evolutionary time. So we've got the most fit robot walking on flat ground over 250 time steps in a simulation. And let's start with the CPG drawn in blue. You can see the metronome at work here. Here's the CPG. It sends a value to the right leg, then a value to the left leg, right, left, and so on. And blue is down here at 0 the rest of the time. The CPG is turned off. Yeah, so there's the metronome. Let's have a look at the hip now. Here's the hip drawn in pink, and you'll notice the label on the vertical axis is motor output. So what the pink curve is showing is the amount of force that's being applied by the motor at the knee, time step to time step. Actually, it's the amount of torque, the amount of rotational force that's being applied. What can you tell me about the pattern of force that's being applied to the knee as this robot walks along flat ground? Is this passive dynamic walking? Is this hybrid dynamic walking? Is this active walking? What would the pink curve look like if this was pure passive dynamic walking? Pink is the amount of force being applied by the motor.
It'd just be flat.
It'd be flat at zero, right? There's no torque being applied by any motor at any time in a passive dynamic walker. The first passive dynamic walker we saw had no motors on it at all. So the fact that the pink curve is not at zero all the time tells us that this is definitely not passive dynamic walking. Is it hybrid dynamic walking or active walking? You typically don't exhibit active bipedal locomotion. You are typically not tensing all the muscles in all your legs all the time. That's why it's called hybrid. Sometimes on, sometimes your muscles are tensed, sometimes they're not. What's going on here in this robot? What would it mean for the knee to be controlled passively in this case? You'll notice that there are brief periods in which the pink curve descends to zero. There are very, very short periods during the gait cycle where the motors at the knee apply zero torque. In essence, the motor just kind of relaxes and says, knee, you're doing the right thing. And then very quickly, the torque comes back on again. So this is hybrid dynamic walking, but it's pretty active. There's a relatively few, very short periods of passive dynamics at the knee. What about, at the hip, we're talking about the hip in pink. What about the knee in yellow? What's going on at the knee in this robot? Passive dynamics, hybrid, active.
Like hybrid for a similar reason, it's just spending more time without leg tensions.
Absolutely. There's more passivity. There's longer periods in which it's at zero or very, very close to zero. These very shallow bumps here, this is a little bit of torque. It's basically the motor just kind of cleaning up or correcting what the knee is doing. You cannot just tense your muscles or relax it. You can tense by more or less amounts. So as you're walking around and most of the muscles in your legs are relaxed, from time to time they tense a little bit and they're kind of cleaning or correcting the gait a little bit. Yeah? Okay, so that's good. This looks quite a bit like what we do. We definitely have much more periods of passive dynamics, but more or less we've got the right thing going on here. Okay. They continued this experiment into phase 4. So in this case, they now started to increase the robustness of these robots even further. The robots are robust. They can walk down a declined plane. They can walk on flat ground. They wanted to now make the robot robust to external perturbations. So they continued evolving for another 100 generations. They were evolving aspects of the robot's body. They're evolving all the synaptic weights that flow from the CPG and the sensors to the motor neurons. But during each simulation, they added wind. So in PyBullet, you can do this as well. You can apply small random external perturbations to objects in your simulation. Remember in phase 1, 2, and 3, the robot was walking in a completely windless, airless vacuum, as your simulated robots are doing. And what they observed during this phase 4 is that the robots could continue walking even though they were being knocked around a little bit by these external perturbations. They mentioned in the paper that the robots developed dynamic mechanisms to adapt to noise. What does a dynamic mechanism mean? It means that dynamically, or there was change to the way in which the robot moved as it was being hit by external forces. Remember the Big Dog video? That was a demonstration that Big Dog can handle external perturbations by dynamically adapting its gait to recover back to the way in which it's most familiar to walk. Okay. When pushed too far to one side, the machine was observed to adjust its foot placement by stepping inward to regain its balance. Not unlike Big Dog did in the initial video. Okay. Here's a demonstration of this robustness to external perturbation. So in the minimal cognition tradition, they took the most fit robot at the end of phase 4, and they played that robot back many, many times in a number of simulations in which the wind increased in intensity. And they measured in each one of these simulations how many steps were taken before the robot fell over. So in no wind, this particular robot can take 38 steps before falling over. In a breezy environment, it continues to take that many steps. But as wind intensity increases and when things get very, very windy, the robot can take 5 steps before falling over. So robust, but not perfectly robust. Okay, phase 5. They continued evolving body and brain. Now they wanted to ensure that the robots were robust to internal perturbations. What the heck does this mean? As they were, every time they built one of the simulated robots in the evolving population, whenever they built it, they made mistakes when building the body. For example, if the robot was supposed to have a length, a lower leg and an upper leg length of L, they'd build the robot such that the lower and upper leg had a length of 0.95 L or 1.07 L. The robot was a little bit shorter or taller than the genome said that robot should be. Here's an example over here. Why would they bother doing this? Why would you ever want to evolve a machine in simulation to be robust to the ways in which it's made?
Is that kind of like trying to mimic, like organic, I don't know how to describe it, but like organisms will vary slightly in this kind of stuff, and the genome has to account for that so that it doesn't get caught out in any kind of difference.
Exactly. Your genome doesn't somehow encode your physiology so that you walk when you're exactly 6 feet tall, because some of you are taller than 6 feet. Some of you are less than 6 feet. All of us used to be less than 6 feet tall. All of us used to be less than 3 feet tall. All organisms need, whatever their adaptive behavior is, that adaptive behavior needs to be robust to changes in your physiology because your physiology changes. So there's a bit of bio-inspiration here. They wanted to see whether they could make machines that are like organisms in that way. Can they evolve to walk even when those machines are, that any one individual machine is a little shorter or taller? They also executed phase 5 here for engineering reasons, not for scientific reasons. What's the engineering rationale for wanting to design or evolve machines to be robust to internal perturbations? Why does this matter?
All your parts aren't always going to be manufactured exactly the same, so you have less variance than biologically speaking.
Absolutely. We're going to spend about 2 weeks looking at a whole bunch of folks attempting to cross the reality gap. take evolved machines and build them in reality. And you can be sure that when any of these machines are built in reality, the upper leg is never going to be exactly L units tall. It's going to be off by some amount due to manufacturing error. Humans cannot manufacture anything perfectly. There's always a bit of noise. So why not, before we even get to the manufacturing stage, ensure that all of these machines are robust to internal perturbations? So they ran phase 5, and then to demonstrate that at the end of phase 1, they now had a population of walking machines that could be built with manufacturing errors and still walk. So here we go. On the horizontal axis here, might be difficult to see. This is the percent error in manufacture, percentage of the body change as a result of manufacturing error. Here's 0% at the left here. The most fit machine at the end of phase 5 could take 40 steps before falling over, and even up to about 8 or 9% manufacturing error, there was no effect on behavior. It was still taking 40 steps and then falling over. And then beyond that, these internal mistakes, these physiological errors started to catch up with the machine. Okay. Phase 6, I promise this is the 6th and final phase of this experiment. They continued to evolve bodies and brains of these walkers to now be robust to CPG perturbation. What does this mean? What they did in this case was, during the evaluation of every robot during this evolutionary phase, they messed with the metronome. They messed with the CPG. They would either make it go a little faster or a little bit slower. So inside the robot, it's moving in response to the CPG, but the CPG itself is no longer perfectly reliable. Sometimes it runs a little bit fast, sometimes it runs a little bit slow. So again, here's the most fit robot at the end of the 6th and final phase of evolution. Let's have a look at the metronome, the CPG, which is these magenta spikes here. It's a little hard to see. You'll notice that at the beginning, the CPG is beating every 35 time steps in the simulation. Why 35? Because for this robot, it takes 35 time steps until its heel strikes the ground for the first time. That's the natural frequency that this robot likes to walk at. It takes one step every 35 time steps in simulation. So you'll notice the horizontal spacing between these spikes is about 35. And then you'll notice that in here, the horizontal distance between these spikes is a little bit less. They're speeding up the metronome. And then in here, the horizontal distance between these spikes is a little bit more than 35. It's a little hard to see, but during this part of the simulation, they ran the metronome a little bit faster, and during this part of the simulation, they ran the metronome a little bit slower for this robot. How did the robot respond? Did it fall over once that started to happen? No. How do you know?
Because the graph keeps going.
The graph keeps going, right? The blue is representing the stride length. It's showing the sweep of one of the legs. How does the robot deal with this internal variability? What does it start to do in here where the metronome starts to beat a little faster?
Shorter strides, make it much like this.
Absolutely. And then as the metronome slows down, what happens?
It also slows down, longer strides.
We're going to end this lecture where we started it, right? It starts taking very long, slow steps. You now have a robot that is robust to wind, it's robust to manufacturing errors, and it's robust to internal errors. Why does that matter?
prepped for the real world.
It's prepped for the real world as much as you can imagine. I know these co-authors, they're paranoid people, right? This is prepare for the worst, every possible bad contingency they could imagine. Now, internal perturbation seems a little strange, right? If we're going to build this robot in the real world, it's going to be controlled by electronics, by Raspberry Pi. Electronics are perfect, right? What's the problem here? I don't get it. Electronics don't fail. They don't slightly speed up or slow down. All the electronics running in our computers for the last 30, 40 years have been designed exactly for that not to happen. So why build in this contingency? Imagine we did build this robot in reality, and there's some circuitry inside, and that circuitry is emitting a signal, and that's going to the motors. What could go wrong inside?
Maybe like the parts can like wear down a bit just from like rubbing against each other and stuff.
In a computer or this, there's not too many moving mechanical parts. So whatever the clock cycle is in a computer or your phone, it's reliable, the electronics is reliable, and it usually lets the machine as a whole be reliable because there aren't moving parts. If you're a car owner or a bicycle owner, you know this, right? Mechanical pieces wear out, things start to slip and slide, rotate faster or slower than they're supposed to. This machine has been evolved to handle some of that, at least up to some degree. Yeah? So at this point, we have a battle-hardened machine, at least in simulation. Optimistically, we might hope that this thing could be transferred to reality, but as we see when we get to the reality gap next week, that's not an easy thing to do. Okay, we've got about 15 minutes left, so we're going to start in on our new module in the course, Open Problems in the Field. And in all of these lectures, we're going to try and start with the problem and then the best solution that's been found to that problem so far. The first problem we're going to look at is a bit of an abstract one. This is known as the genotype to phenotype mapping problem. What is a G to P map? Most of what we've talked about in this course so far are genotypes, which are strings of numbers. That's what you're using in A10, in assignment 10. And the phenotype is the way in which the robot moves. The mapping is pretty straightforward. It never changes. You take the numbers, you put them onto the synapses, you run the robot, and you always get the same thing. Turns out that in reality, there is a very, very complex mapping between your genetics and you, your physiology and what you do. There is a very complicated mapping that happens, and it happens for a reason. Typically, during evolution, mutations are random. They go in and they hit some particular part of your genetics. The effect, the mutation at the genome level is random, but the effect on your phenotype is not random. This is an example of the genotype-phenotype mapping in you doing good work on your behalf. If any small random change happened to your genome and you had a direct mapping, there was suddenly a random effect on your phenotype, that's a very bad thing. Why?
Most of the time in nature, you probably wouldn't survive.
You wouldn't survive. You are a very highly tuned, high-performance machine. Any random change to the machine, probably for the worse. Random mutations have non-random effects. You might be a little taller. You might be 1/10 of an inch taller or shorter than you would have been without that mutation. But everything else in your body is still proportional. It's not that this part of you is taller and all the rest of you is as it should be. That's not a good thing. So there is a very complicated mapping that itself has evolved over billions of years to ensure that changes that happen down here don't have random effects up here. When we do evolutionary robotics or evolutionary algorithms, we tend to have a very straightforward mapping, which means, and you're going to see this in assignment 10, when there's a random change to a value in a genome describing your robot, there's probably going to be a small random effect on the way it moves, which means most of the time that mutated robot is going to move slower or stumble earlier. So there is a very real need in evolutionary algorithms to make more complicated mappings that ensure or increase the chances that random stuff that happens here, it minimizes the chance of it being bad here. We're going to look at two algorithms in lecture 13, the NEAT algorithm and the HyperNEAT algorithm, that have a more complicated mapping. You'll notice as we go through lecture 13, the genome is going to look pretty familiar. It's going to be a string of numbers, but the way that string of numbers is turned into a robot or a neural network or whatever it is this thing is specifying, that transformation or that mapping is going to become more complicated. And it's going to become more complicated for a reason. The reason or the problem we're trying to solve is to ensure that changes here reduce the probability of bad things happening here. So far, so good? Okay, let's start in and have a look at this. Okay, we're going to start by looking at the problem with a direct mapping. Okay, you'll have to remember back to our discussion of neural networks. When we introduced neural networks, we started by looking at a neural network that encodes and a neural network that encodes OR, and then we looked at a neural network that encodes more complicated functions like exclusive OR, 0, 1, 1, 0. Okay. In those neural networks, there were two input neurons. We could supply a 1 or a 0, or a 1 or a 0, and then we looked to see what arrived at the output layer. If we were trying to evolve the synaptic weights in the neural network to be an AND gate, then the output should only light up when both input neurons are set to 1. If we wanted this neural network to act as exclusive OR, we should see the output neuron light up when only one of the input neurons is turned on. Sound vaguely familiar? Maybe? Okay. All right. So imagine we're doing exactly that. We're going to evolve sets of synaptic weights. We've got a genome which is 1, 2, 3, 4, 5, 6, 7, 8, 9 synapses long. We're going to evolve 9 weights for these 9 synapses, and the fitness is exclusive OR. The output neuron only lights up when one and only one input is lit up. Imagine we decided to put 3 hidden neurons inside these neural networks, and off we go. Okay. Imagine that these 2 neural networks exist in the population partway through the evolutionary process. Both of these neural networks are doing an okay job at embodying the exclusive OR function. You might remember that one way that neural networks can embody exclusive OR is that one hidden neuron evolves to be an AND, and another hidden neuron evolves to be an OR, and the outputs of hidden neuron 1 and hidden neuron 2 and an OR are combined at the output layer, and if you get the synaptic weights right, you can get exclusive OR. Who said that hidden neuron 1 has to be the AND and hidden neuron 2 has to be the OR? It's equally possible that neural networks start to evolve where in one neural network, hidden neuron 1 is starting to evolve the ability to do OR, and hidden neuron 2 is evolving the ability to do AND. Both of those two hypothetical neural networks, one that starts to evolve AND on the left side, the other one that starts to evolve AND on the right side, both of them could be doing an okay job at exclusive OR. That's known as the competing conventions problem. Maybe in you, eye color is 1/3 of the way along one of your chromosomes, and in your future mate that you're going to produce offspring with, for that mate, eye color for him or her is 2/3 of the way down one of their chromosomes. That's a very bad situation, because when you produce an offspring and Mother Nature starts to mix your genetic material, you've got eye color in 2 different places in the 2 different genotypes, and that's going to be problematic for your prospective child. Luckily for humans, eye color in all of us is at exactly the same place on the chromosome, as is every other physiological trait that you have. That makes things very easy for Mother Nature when she goes to combine genetic material from 2 parents, because Mother Nature literally lines up the chromosomes, and eye color is always at the same position, and Mother Nature randomly chooses the allele from one of the 2 parents. The child either gets brown eyes from you or green eyes from your mate. Yeah? So in typical neural networks, if you just allow them to evolve at will, they might start to evolve to do what you want, but different neural networks in the population might start to evolve different subfunctions, like and, at different places in the hidden layer. That's represented in this cartoon here by these different colors. Let's imagine that whatever this person is evolving these neural networks to do, these neural networks have to solve 3 subfunctions at the hidden layer and then evolve synaptic weights that combine those sub-solutions at the hidden layer into the final solution, the thing you actually want. Imagine both of these neural networks are doing a pretty good job at evolving this function, but they're evolving these subfunctions at different places inside themselves. Let's imagine further, and this is often the case, that maybe this neural network is doing a little bit better at and a little bit worse at or. This one is doing better at the other one. One is good at and, bad at or. The other one is good at or and bad at and. They're not highly fit yet. They're on their way to evolving exclusive or. They've got different subfunctions in different places, and some of them are getting better at different subfunctions. Wouldn't it be great if we brought in crossover, and crossover cut these 2 neural networks in half and took the 2 halves and glued them together to make a 3rd neural network? And it happened to do so in a way that brought the pretty good and from parent 1 and the pretty good or from parent 2 together. This is one of the reasons that sex evolved in nature, is that by randomly crossing over genetic material from different individuals, just by chance, sometimes offsprings benefit by getting the best of both worlds. They get things that both parents are good at, combined into an offspring. Okay, so let's imagine that we randomly cut these neural networks with straight lines. We're going to make things simple for now. We're just going to cross them over in a simple way. You'll notice that with any straight line, there is no way that you can cut these 2 neural networks and glue them together and get A, B, and C in the child. Something gets left behind. Here we're going to cut through here. Let's say we cut between A and B in parent 1, and we're going to cut between C and B in parent 2, which would give offspring 1, A from parent 1, and B and A from parent 2. Offspring 1 ends up with A, B, and A, 2 copies of subfunction A. This offspring got 2 copies of the eye color gene. Not such a good thing to have. Assuming that C is a necessary solution to whatever these neural networks are evolving to do, this offspring is at a disadvantage. It has no C. If we cut through here and we cut through here, the second offspring gets C from parent 1 and B and C from parent 2 and ends up with C, B, C down here. Also not good. It lost A. This isn't working very well. Even if these 2 parents, some of them are doing better or worse at A, B, and C, there's no way to combine these together, at least in a simple way, to produce an offspring that has one copy of A, one copy of B, and one copy of C. This competing conventions problem is making a mess for us. We can't have a very straightforward genotype to phenotype map and get this to work. Sex will not work in this case. Question?
When the cut is made on one, do they have to be in the same place?
Good question. So in this cartoon example, we're keeping it simple. In reality, not. We could cut parent 1 like this, and we could cut parent 2 like this if we want. I forget in this cartoon there may be a very complicated way to cut in which you get at least one offspring ends up with A, B, and C, but it's difficult. And if we're cutting at random, the probability goes down and down and down towards 0 that there's going to be any pair of cuts that brings together everything an offspring needs from both parents. That's the competing conventions problem. Remember that in evolutionary robotics and evolutionary algorithms, we're always evolving populations. And sometimes we include crossover in sex because we're hoping that sometimes different individuals start solving different subproblems. One robot walks well with its left leg, but limps with its right leg. Another robot walks well with its right leg, but limps with its left leg. In theory, there might be a way to cut to bring these together into an offspring that has no limp. Very difficult for this to happen in reality because of the competing conventions problem. So years ago, 24 years ago now, the HyperNEAT algorithm was introduced, still in use today, very powerful, very useful. We're going to introduce the HyperNEAT algorithm. It starts by complicating the genotype to phenotype mapping to try and reduce this problem. Okay, here we go. Let's start with G. Let's start with the genome. It's still a familiar data structure. We have a list of things. In this case, we don't have a simple list of synaptic weights. We have a list of groups of 5 numbers. Each grouping here, there are 6 of these groupings. Each one is still responsible for describing a synapse in a neural network. The first 2 numbers inside each grouping represent which synapse it is. So this synapse connects neuron 1 to neuron 4. So this set of 5 numbers describes the behavior of this synapse. This grouping here describes the synapse that connects neuron 2 to neuron 4, neuron 2 to neuron 4, and so on. So we have a list of quintuplets. We've got a list of 5 numbers that describe all of the synapses. Inside the genome of the HyperNEAT algorithm, there is a second separate list inside the genome. You can think of this as 2 separate chromosomes. The second list represents the number of nodes or the number of neurons that make up the neural network. So this list describes the neurons. This list describes the synapses. Let's unpack the name HyperNEAT here. So the N and E stand for neuroevolution. So we're going to take a step back from robotics for a moment. The HyperNEAT algorithm was designed originally to optimize or train neural networks. So we're going to evolve neural networks. We're going to see in a moment that there are mutation operators that can act on the genome, mutations can randomly change any of these numbers. There are additional mutations that can add or remove elements from either lists. If a mutation adds an element to this list, what happens to P, the phenotype, the neural network? In this particular genotype, it's encoding a 5-neuron neural network, which you see down here. If this genotype produces a copy of itself, and during that copying process, there's a mutation that adds a node 6 here, what happens to the phenotype of that child? Is the phenotype of the child the same as this phenotype, the phenotype of the parent? Why not? What's different?
There's an extra synapse.
Not an extra synapse, there's an extra neuron, wherever it is. Now, that neuron is hanging in space. in that child, there's no synapse connecting any of the original 5 neurons to this new 6th neuron. So that neuron isn't affecting behavior. We have a genome that just underwent a random mutation. In the child, a 6th neuron was added to its neural network, but there are no synapses that go into or out of that neuron. So there is no change to the behavior of the neural network. There's been a change to its architecture. There's a 6th loose neuron, but there's no change to its phenotype. Already, by complicating the mapping, we've introduced neutrality. There can be genetic changes that have no effect on phenotype. Turns out that that's true in us as well. There are many, many, many places within your chromosomes where random changes can occur, and there's absolutely no impact on your physiology or your behavior. Okay, I think we'll leave things there for today. You have a quiz due tonight. You're working on A10 or D5. Have a great rest of your week.